So welcome to our seminar series in the Gemini Center on Quantum Computing. Our speaker today is Alexander Müller-Hermes. He joined the operator algebra group at the University of Oslo as an associate professor in October this year. His research is on mathematical aspects of quantum information theory with a focus on quantum Shannon theory, entanglement theory, and their interplay with operator algebra. Alexander obtained his PhD in 2015 from the Technical University of Munich, where he worked as a postdoc at the Center of Mathematics and Quantum Theory, QMath, at the University of Copenhagen until 2019. From 2019 to 2021, he was a Marie Sklodowska-Curie Fellow at the Institute of Camille Jordan at the University of Lyon 1. So today he will speak about fault-tolerant coding for quantum communication. And if you're ready to take it from here, you're free to speak.
Yes, okay. Yeah, thank you for the kind introduction. So indeed, I started last week as here in the math department. And okay, I mean, now there are not so many of you here, but so I'm looking forward to, of course, meeting people from the center or people interested in quantum also in person at some point, maybe in the near future. So indeed, so I will talk about some recent work with Matthias Christandl from Copenhagen. And this is like very much physicsy, so Nadia and Sergey, be warned. But yeah, so got fault-tolerant coding for quantum communication. So let me maybe first start a bit informal. Can you see this? So why do we need quantum communication? So that's maybe in the distant future, maybe not tomorrow or next week. So we could envision these two scenarios where so one scenario is like this quantum networks that people are actually trying to build, yeah, also now, where you have like cities where you have like quantum computers or quantum computing labs, and you want to connect these labs and establish entanglement between these locations. There are certain applications that people are looking into where such entanglement over long distances would help. And this is, of course, one scenario where you want to communicate quantum information, so share entanglement. And another application would be for quantum computing, like if you have envision like a quantum computing chip where you have maybe two quantum cores, so like CPUs, just maybe QPUs or something, then these two cores could also use this, could send quantum information between them to share some computing task. These are maybe the two scenarios that you could have in mind if you're interested in actual application. So for my talk, I will focus on like a slightly more simple setting. So I will consider this setting where you have maybe two quantum computers, quantum computer A and quantum computer B, that want to communicate, let's say. So they want to communicate either classical or quantum information. I will mostly focus on quantum information in this talk. And they can do this using some physical communication channel. You can think of a channel transmitting qubits. So some qubits are transmitted over some fiber optical cable maybe. And we are interested in this question of what the maximal rates of communication are for reliable information transmission. So a rate of communication is like, I want to say like something like, how many qubits can you transmit per channel use, or how many classical bits can we transmit per channel use? And this we want to do reliably. So like the scheme should not have a high probability of failure. And maybe which differs from, or what differs from previous work is that we want to do this under realistic assumptions on noise. So let me say a bit about this realistic assumptions here. So there are 2 points in this communication setup where noise plays a role. So first of all, there's this physical communication channel which if you think of some long fiber optical cable connecting Oslo and Copenhagen, this will of course have some noise. So one type of noise, so you can think of this noisy qubit channels here, and the type of noise that you can have in mind for this talk might be this depolarizing channel of strength P. So you input like a qubit state, and with probability P, it is transformed into the maximally mixed state. So it's completely depolarized. And with probability 1 minus P, it is not altered at all. So this is like a common noise that is considered in these kind of settings, and I will say a few words about this in a few slides. There's another setting of noise that is usually, or another noise, form of noise that is considered in quantum computing, which is the noise affecting these quantum circuits. So think of these quantum computers as executing some quantum circuit, and of course, what we know is that this execution cannot be completely flawless. So one model of noise would be that each logic gate that you execute has some probability Q of failure. Okay. So we want to consider these communication settings taking into account both of these forms of noise. And typically we can expect that this noise Q that affects the quantum computer is much lower than noise P affecting the physical communication line, since this line is somehow a long, uncontrolled wire where the quantum computers are somehow labs that are shielded against noise. So our objective is to send information with final error rate as small as we want. So that's like the key figure of merit here. So we don't want this error rate to depend on either P or Q. So maybe what it will depend on is the error rate of your classical computer that you use to control these systems. Okay, so there are two ingredients that we will use to achieve this objective. And the first ingredient is quantum Shannon theory, which I will explain in a second. The second ingredient is fault tolerance through quantum error correcting codes. I will also explain this. For those of you who know this, I don't know whether any of you knows much about these two things. This combination is somehow more challenging than you would expect. So, as I will explain towards the end of the talk. So let me start by explaining you a bit what quantum Shannon theory does. So quantum Shannon theory is the study of exactly this problem that I talked about before. What are the optimal communication rates for communicating information over noisy quantum channels? So, and what you look at is this scenario where you have a message, which is state of n qubits, and you encode it into maybe many more qubits that you then send over this noisy communication channel. This noisy communication channel distorts this information in some form, but by choosing this encoder properly, you will, there might be a decoding quantum channel that gives you the message back with some error epsilon. So usually we don't want to focus on a single message, but we want to somehow consider like a uniform error over all possible messages. Or to say it differently, we want that this whole communication setting or communication or coding scheme, as we call it, approximates the identity channel. So the identity channel on n qubits. Okay, so is this more or less clear? This the setting that I used?
Yes, I think so. Could you say what this DM, the T, and the EM is?
Yeah, T is always my noisy communication channel. So TM is this, and by DM and EM I will denote the decoder and the encoder. So E
okay, yes, thanks.
So okay, so I will always compare this coding scheme to the to the completely noiseless channel, so the identity channel. And I will. Oh, was there a question or?
Are they? I mean, you minimize the norm. What are they? So like just operators, matrices. What are they? The DM and the EM.
They're quantum channels.
Quantum channels.
Yeah. So, I mean, yeah. Maps between matrix algebras. So, completely positive trace preserving maps. So, by minimizing over these coding channels, or this encoder and decoding channels, I can introduce this optimal coding error. That's like the optimal error I could achieve using m uses of the channel and by sending nm bits of information. And I can look at these achievable rates. So these are like numbers R that I can obtain as limits from this sequence nm over m. So number of qubits sent per, over the number of uses of the channel, such that this optimal coding error goes to 0. So such that I find sequences of these quantum channels making this norm vanish in the limit. So these are the rates of communication. So they somehow like quantify how fast information can be sent over this channel, or how much, to put it a bit differently, how much redundancy I have to add here to retrieve this information. The capacity of a quantum channel is the supremum of these achievable rates. It's like the quantity quantifying this like, yeah, how good the channel is. So let me point out this theorem by Lloyd, Shaw, and David, which is really like a landmark result in quantum information theory, which gives a formula to compute the quantum capacity. And this formula is not super important what this quantity is, but it gives this number, this supremum, as a limit of an entropic expression. So this coherent information is like a function involving entropies that you can compute using this channel. Unfortunately, you need this regularization, so you need to input like a tensor power of the channel. But so the take-home message from this is that we have a formula for this, and in principle, we know the coding schemes that achieve this. So we know the sequences EM and DM that will lead to rates that are close to this capacity. So let me tell you how these coding schemes look like, or these encoder-decoder pairs. Just basically a bit hand waving. So the encoder-decoder pairs that we know, so that I would use to prove this theorem for you, would look like this: that you take these n qubits and you use an isometry to embed this n qubits in some high number of qubits, of a high number of qubits. And then you apply a unitary that you can choose random from the unitary group. And somehow it's a random construction. So the statement will be that then with high probability, this will be a good encoder. So what you see here is that this state that you will input into the channel is a highly entangled qubit state, or highly entangled quantum state on m qubits. And it is not so easy to implement this scheme, maybe. So you need to apply like a unitary to many qubits. So I should point out that there are also different constructions of these encoders that are efficient in the sense that you have a polynomial-sized quantum circuit to do this. The keyword here is quantum polar codes. But again, like they are complicated circuits that you will not be able to implement on like your qubits without like some fault tolerance or some quantum error correction. So they are difficult to implement. For the decoder, the situation is even more, a bit worse, that the general techniques only give existence of decoding channels. And if you do specific constructions, like for these quantum polar codes, they are in general not efficient. So they will not even be like a polynomial-sized quantum circuit. So it's not even clear like how to really implement them. But this will not be so important for this talk. We are really interested in basically existence is enough for us. There's a different problem that I will now get to that we solve. Okay, so there's no hope to implement these coding schemes without fault tolerance. So let me tell you a bit about fault tolerance. So fault tolerance solves the basic problem of how to run a quantum circuit on a noisy quantum computer. By quantum circuit, I mean a composition of elementary operations. So these are unitary. So somehow, like in quantum algorithms, you take a bit of a different viewpoint, where you look at so-called closed quantum systems. So you use unitaries acting on pure states usually, whereas in quantum Shannon theory, we often use like open systems where you have like quantum channels interacting with an environment, but they are somehow equivalent. So these elementary operations, for this talk, you can consider that they are the single qubit gates X, Y, Z, T, and H, 2-qubit gate C0, the C0 gate. You have the identity gate, which models the qubit at rest, which the mathematicians among you might not understand why you would point this out of the gate, but we'll come in a second. Then you have preparations and measurements in the computational basis, and partial traces, so you can throw qubits away. This set of elementary operations that I've given here is a universal set in the sense that this is a dense set in the set of all quantum channels. So whatever quantum channel I give to you, you can approximate arbitrary value using compositions of these elementary operations. An example of a quantum circuit is this teleportation circuit, where, where you start with some preparations, does some measurements, and some gates conditioned on classical measurement outputs. Here I use these identity operations that are maybe a bit puzzling to have these kind of time steps. So sometimes I have a qubit that doesn't do anything, and then I'm formally putting there an identity operation. So it's a qubit that doesn't do anything. This is now important if we want to model noise for this quantum circuits. So this is like a noise model that is called Pauli IID noise model, which is not perfectly realistic, but it's at least like a realistic model, or it's a model that is considered in this quantum error correction literature. So this works like this: that after each time step, you insert this kind of depolarizing channel on each of the lines. So each qubit goes through this depolarizing channel, and where Q here is a small probability. Typically, it's small. Right. So this is a noise model. So
Alexander, can I ask just a short question? So when you say qubit gates, you view them as channels, you mean really the operation of conjugation by unitary or?
Exactly, yes. So so this is like it's a bit of one has to get used to the like somewhat two slightly different ways of thinking about this. Okay, yes. So this noise model, right? This will be very important. So you really introduce this DQ channel on each of these lines after each time step. So you see that somehow this noise will accumulate over time. So you will produce more and more noise on your system. And it's not clear at all that you can somehow run useful computations under these noise models. So this problem was solved by using quantum error correction. So somehow the basic idea of this, I'm not going into details, is that you combine several physical qubits into logical qubits. So these logical qubits are qubits in a quantum error correcting code. So for example, there's this code, it's called the 7-qubit Steen code, where the computational basis states are built from 7-qubit states. So here, if you count, they are like seven qubits put together to form one logical qubit. This 7-qubit Steen code protects against any 1-qubit error. So if you apply a single quantum channel to any of these qubits, you will be able to correct it in the end. And moreover, this code allows for convenient implementation of elementary operations. So if I want to, for example, run a C0 gate on the logical qubits, then there's a very convenient way of doing this by running certain elementary operations on these 7 qubits. So this is an important feature of these quantum error correcting codes used for computation, that you can do the elementary operations in a convenient way. So once you have have a code like this that you want to use, you can concatenate it to get better protection. So I can use 7 physical qubits to form 1 logical qubit. Then I can take 1 or 7 logical qubits and make another logical qubits out of them. So this is called a level, right? So I have a first level where the physical qubits are put into 1 logical qubit. Then I get another higher level of this concatenated code family. And this I can iterate to get better and better protection. Now, the problem that is solved somehow by fault tolerance is that here, by doing this, you get more and more qubits, right? So somehow you get more and more locations where you have to apply this noise channels. So from this, it's still not clear that somehow you can actually run algorithms because you get more errors also. But this is exactly what you can show. So this is called the threshold theorem, and this is a landmark result for quantum computing. So my terminology here is like this. So if I have a circuit gamma, then I can implement the circuit in the concatenated code at level L. I will denote it like this. So gamma subscript CL. And then I can apply this Pauli noise model onto this encoded circuit, where each physical qubit, each physical line is hit by this depolarizing channel of strength Q. Then the threshold theorem says that there exists a number Q0 such that this encoded quantum circuit can be made arbitrarily close to the ideal quantum circuit if I choose a high enough level and if the strength of this error, so the strength of this depolarizing noise, is below this threshold. So there's some small number Q that if I'm below this threshold, I can increase the level of this concatenated code, and this whole right-hand side will go to 0. So in other words, I can run whatever circuit I want if I have a high enough physical qubits at my disposal, and if the physical qubits have somehow a noise rate that is below this certain value. Okay, so that's like an important result in quantum computing, which actually I think initiated this whole research area in a sense. Okay, so let me summarize. Oh, sorry. Let me summarize. We have now these tools from quantum Shannon theory, which can give you encoder and decoders to send information over a noisy channel. You can make this error epsilon as small as we want, but the assumption is that the encoder and the decoders are perfect. There's no noise affecting them. On the other hand, we have fault tolerance, where we can run a quantum circuit within a quantum error correcting code, such that it will approximate an ideal quantum circuit with an error as small as we want to have it. But the assumption is that the noise rate Q is below this threshold, which typically is very small. Now, let's combine these two things for this communication problem. So we can always assume that the encoder and decoders are quantum circuits because the quantum circuits are dense in the set of quantum channels. Then the naive approach might be to just use the threshold theorem for this picture that I drew here. The first problem is that this noisy channel is typically much more noisy than what you want for the threshold theorem. So if it's a long communication line, this is too noisy to apply the threshold theorem directly. So what you would need to do is you want to apply the threshold theorem to these coding circuits, but then if you implement them in the error correcting code, the output will be logical qubits. They will not be physical qubits that you can send through a channel. So somehow you will prepare a code word or like an input for your physical channel, but it still sits in the code. And the same is here on the other side, where the output of the channel will be physical, but you somehow have to get it into the code to start with. So there's somehow a problem that one has to bridge here. Another approach might be to make an entirely new code by combining this concatenated code construction and the quantum channel code. But then somehow, so at least if I think about it, you would have like a lot of qubits, because these are qubits coming from this concatenated code. So there will be an exponential number of qubits coming out here, and that you want to send through the channel. There's a huge number of channels needed here. So it's unlikely to achieve high communication rates. So what we did is somehow maybe a mix of both in a sense. So our approach uses like a gadget, which is like a logical to physical interface circuit. So there's a quantum circuit, and I will not go into details of how to construct this circuit, that takes you from the nth level of the concatenated code to a single physical qubit. And such circuits exist in both directions, so I can also go from the physical qubit into the nth level of this concatenated code. The important property here is that this noise, if I introduce noise on this interface, so of course I should put the same noise here on each gate in this interface circuit. So after each gate, I want to apply this depolarizing channel of strength Q. Then it will be close to the ideal interface up to an error that is linear in this gate error rate, with a constant C that is independent of L. So let's go through this a bit. So this is really like the best you can hope for this interface circuit. And that's easy to see because you are decoding, or you go from this nth level of the concatenated code to a single physical qubit. So in the end here, you will apply maybe a single qubit gate. So there will be you will get you have a probability of Q that there happens an error in this last step, right? Because you go down to a single physical qubit, which is affected by the same error here. So the best you can hope for is that you get a linear scaling in this gate error rate Q. It's not trivial that you can actually do this, but this is what comes out of this construction. Okay, so with this construction, you can define an effective communication channel. So this is a channel from your logical qubit to the logical qubit by going through this interface circuits and over the channel T. By what I said before, so this noisy interface is close to the ideal interface up to linear error in the gate error rate. This means that your effective communication channel will be a convex combination of your channel T, now viewed as a channel between these logical qubits, and some other channel N. So this channel will be close to the channel T if the error rate Q, this gate error rate Q is small. So now I can consider a coding scheme for this effective channel instead, and I can achieve rates that are larger than the capacity of the effective channel minus some delta. Remember that the capacity was a supremum of achievable rates. Then I can use that the capacity is a continuous function in the channel to replace it by the capacity of the channel T, and I get some function that depends on this continuity here, which is explicit but slightly complicated, that goes to 0 as Q goes to 0. Note that this effective channel is close to the channel T, with an error linear in Q. And that's it, right? So now this shows that I can achieve rates that are close to the quantum capacity. So this is now maybe what you should take home here. This is the basic idea of this construction. If you go through the details here and make this mathematically rigorous, then it's actually quite more complicated. And the reason is that I swept a lot of things now under the rug. And this is maybe only maybe I go quickly through this because it's, maybe only for people who know a bit of quantum error correction or the details of this. So what will happen here is it's a bit more complicated than what I just said. So what happens is that in these error correcting codes, you will typically get a lot of correctable errors. So the state that you prepare here, that you want to send through the channel, it will have a lot of correctable faults on it. So if you want, you can expand this as a convex combination of fault patterns where these depolarizing channels act. Then these correctable faults will be correlated because this quantum circuit uses some 2-qubit gates. So the 2-qubit gates will usually spread correctable errors, will lead to some correlation here. If I now map this state to single qubits, there will be events where these interfaces get a lot of noise, which means that this final qubit state that I get here, this many qubit state, might correlate along these applications of the channel. So to put it slightly different, if you properly analyze this, then what this leads, or what this transforms to this whole setting, is an ideal quantum channel and some effective environment that is also an input to your effective channel that is a correlated quantum state. And your effective communication channel will connect to the qubits of the ideal circuit and this effective environment, which is very correlated. You can use, so what we do is then we use some trick to relate this effective channel to an actual qubit channel, which then you can view as the effective channel that I stated before. This channel will be a convex combination of the channel T and an depolarizing channel. And this is also the channel that you then develop the code for. Okay, this just as a side remark. Look in the paper if you want to see the details of this. With this, I want to just repeat our results, like the proper results. So what we show is that there exists a threshold Q, 0, such that any rate R that is greater than this horrible expression is achievable using coding schemes affected by this Pauli IID noise of strength Q. And this here is this expression popping up in the capacity. So you obtain the capacity by taking the limit of k going to infinity here. Another technical side remark is this term, which still depends on k, which means that you cannot take the limit of k of this formula, which is again a slightly technical thing you need to fix. So this is like the rates that you can achieve if you fix the gate error rate Q. Somehow the more qualitative statement is the threshold theorem for capacity, which says that for every quantum channel T, there exists a threshold Q such that any rate R that is greater than Q minus delta, or the capacity of T minus delta, is achievable using coding schemes affected by Pauli IID noise of strength Q that is less than the threshold. So this extends the usual threshold theorem to the setting of capacity. And with this, I want to thank you for your attention.
Thank you very much. Thanks for the nice talk. I guess I have at least some obvious questions.
Okay.
And I will just start with one, and everybody else can just after this also ask their questions. So the natural question to ask, you have looked at one type of noise. Does this somehow generalize to other types of noise easily, or would that be very hard work?
No, yeah, so actually in the paper, we look at more general types of noise. So we look at basically, I think that I think we are convinced that this extends to the types of noise where the threshold theorem holds. So these are also include some correlated errors. If you have like, but you need certain assumptions on this. Maybe like that the correlation decays like sufficiently fast. We have not. So I think. I would say we have not rigorously proven that this is actually the case, but we are quite sure that it does. What we have rigorously proven is that if you use IID noise, where you don't, so let me jump to. yeah, if you use IID noise or noise where you don't get correlations, additional correlations along these wires where the channel acts, then this also works. So particularly if you have a coding scheme that doesn't use much correlation between these wires, then you can even allow for more general noise models on the quantum circuit.
Okay.
So, yeah.
Are there any other questions?
Yeah, I have a question. So coming from a computer science background, I was glad that I could follow some of this at least. But you're talking about a communication channel, and you said that it could be a wire. So what kind of assumptions are you making with respect to the communication channel?
Yeah, this is a good question. So the usual assumption is that it's IID. So that I'm not, let me think of, yeah, I think, yeah, I mean, our usual assumption is that it's an IID channel. There's no correlation between the channel uses. Does this answer your question? So, I mean.
Yeah, I was more thinking.
Physically, or?
Yes.
So I mean, if you want to, yeah, have an example, maybe you can, what would be a typical example? Yeah, maybe if you use like a fiber optical cable and you send photons and you encode some qubit in these photonic modes, but such that there's no correlation between channel uses. So we don't want, so what we usually don't want is that you, I don't know, if you fire your photons very quickly through the channel, it might be that two uses of the channel become correlated. This we don't want. So usually, like the usual setting is that the channel is IID, which is an ideal. I mean, it's an idealistic assumption, but it's a common assumption in quantum channel theory. There are so there are some other assumptions that you could make where our results might extend to, but I have not looked into this. Is that if you have a jammer that tries to jam your signal, that's another common assumption, or like a wiretapper that tries to read your information out along the way. So there are other communication settings where someone tries to intercept your photons or something. I'm not
okay.
so.
Yeah, and then the benefit of like, since you're able to encode the quantum state, you will then be able to transfer a lot more information per item than you would in a classical case. Is that correct? So what I'm trying to get at is like you're investing a lot of qubit resources into kind of making sure that the computation is error-free. And then the other thing we could do would be, of course, to invest those qubits into computation and then transfer stuff classically, because then we know that we will get some information there eventually.
But are you thinking about like this on-chip example that I mentioned in the beginning, or what do you have in mind? Because
I think this is fundamental, right? You can use more resources for computation, or you can use more resources for communication. Yeah, and then in your case, enabling communication seems to be quite like enabling communication in the quantum domain seems to be quite expensive in terms of resources. So I'm just trying to I'm wondering about how that trade-off works out.
I guess, I mean, for specific applications, you have to, I mean, you have to look at this trade-off more carefully. But I mean, there are applications. So for example, there's an application where you have okay, it's very, very different from quantum computing, but so you have an array of telescopes where you look in the stars, and there's an application where you use entanglement between the telescopes to make it noise resistant, an array of telescopes. And this is a problem where you need to establish entanglement between distant locations. So in this sense, there you need quantum communication. So it's no way around it, because you won't have entanglement between these distant locations. So there's no way around this. If you want to send classical information, So then, okay, and then you can ask whether it's worth to spend this qubit resources. And then I don't know. Like, it depends on the specific application. But I think, I mean, there are applications also if you want to, in a quantum computer, run algorithms on like dual quantum core, if you envision this, then you also want to have entanglement between these cores. And to establish this, quantum communication protocols will help you to minimize the resources. You also have like, yeah, I think that's like the take-home message. Okay. Of course, you can. Okay, if you want to, maybe you have the somehow a more NISQ, like the noisy intermediate state quantum computing paradigm in mind, then maybe, I mean, maybe you don't want to invest that much resource into making everything noise free. But then I would still argue that you can, yeah, I mean, this trade-off will be somehow non-trivial. I would guess, where you maybe can use some communication protocol on a noisy computer, yeah, where you might gain something, and then using non-trivial codes can still help you, I think. So there are a lot of
yeah. Thank you. I don't think I fully understand my own question even. So,
okay.
but yes, so my takeaway is that there's for sure a trade-off here, and it is to a large extent application dependent.
Yeah, so I think what our main motivation was to show that because in quantum channel theory, you want to make the error, this final error, arbitrarily small. And somehow the message, what you read in books, is always that you have these capacities which are fundamental constants by which you can achieve these communication rates with an error that you can make arbitrarily small. But nobody has before looked at noise affecting your coding schemes, because classically this problem doesn't occur, because classically the classic computers are so noise free that you will not see this in any setting. So
that's actually incorrect. There's lots and lots of noise in classical computers, and we use error correcting codes like for banking applications and stuff. All memory items have error correcting codes.
Okay, yes, but you're maybe not using it if I send information through the internet that has to be not stored very long, or do you?
There are lots of channels that are unreliable, like wireless, for instance, and then there's always a trade-off of whether you want to do error correction, which is more costly, or error detection and resending.
Oh, but you are doing but this is the channel that you're coding for, right? Or that you're correcting?
This happens at all levels, but in wireless networks, it happens at the physical level, because like everything can happen in air.
Yeah, but usually, I mean, my laptop doesn't use, doesn't have an error correcting code running on its RAM or running on its memory when I send information to the wireless network. Or does it?
No, it gets added by the wireless adapter before the transfer. Yes.
Yeah, I mean, but that's what I would call a channel code. So that's what I call a code that you add to. Yeah. Okay. Maybe we don't have to have this conversation now in detail. I mean, yeah. Usually your memory on my laptop, is this correct? I mean, that my memory on a laptop doesn't have error correction.
Yeah, on your laptop, that's correct, because this is a fundamental problem, right? Errors can happen. They are very small. The probabilities are very small for classical computers, but they're still there. And memory corruption happens all the time. It's just that in most applications you don't notice and you don't care. But if this is why banking examples are good, because if your balance, if you flip a bit in your bank balance, that can be a big deal.
I agree. Yeah, but so I think our take-home message is that even that the memory of the quantum computer would need to have a fault tolerance, would have to have fault tolerance built into to even send information through the wireless. It's not enough to only have the wireless adapter adding a code, but also your computer has to have a code, and somehow it's about the interplay of this two. That's what, I think what the take home message.
Okay, thank you.
I would be happy to discuss this more, because I would like to learn more about classical programs.
Yes, let's do this afterwards. Are there any more questions? If not, then thank you very much, and see you next month.